So this here circuit is a figure from the book. This is figure 17.50, and as you can see, we have an AC power source of 60 volts angle 0 feeding a series parallel circuit here, which seems to be a bit of a jumbled mess. And they're asking us to find the supply current and the total impedance as seen by the supply. And so the first thing you really need to do with something like this is you come in here and label your nodes. Okay, so I'm going to label my nodes. So this is all node A. And I'm going to change color. I highly recommend also changing colors. So here we have this magenta color. We'll call this B. And I don't know, go to a green color and we'll call this all C. So the first thing we need to do here is just simply redraw the circuit. Okay, so we've got this labeled. So this is point A up here. And so I'm going to come down and I have a R1, which is 2 ohms, coming down this way. And then I'm going to have a capacitor. So that's going to be minus J 2 ohms. And also over here looking at A, right? And we went through here, and I didn't actually label all of these, but I labeled the main ones here so that you could see. So this is going to be R2, which is 3 ohms. And then there's a capacitor of C1 here. This was actually C2 over here. So there's a capacitor here, C1, which is minus J 9 ohms. And there's actually also an inductor here, which is plus J 6 ohms. And then coming down this way, we have R3, which is 10 ohms, and that is all connected to C. Okay, so let's just kind of double check here. So we see that we have this inductor over here, which is attached to point C. So this is all point C down here. We have the capacitor C2 is attached to point C down here. And we have resistor R3 right here is attached to point C. Okay, so this is all point C. I had point B was between R2 and C1, right? So this was what I had labeled point B. Okay, and so there's all my points. All right, so this is the circuit, but it's a lot more readable and workable now. So as we kind of come along here, right, we can kind of see now we have we have an impedance here, and then we have another impedance here, and we have a third impedance here. All right, so you know, we'll call this like this is going to be Z1, and this is Z2, and this guy is Z3, and so these three impedances are simply in parallel with each other. So Z total now is 3 parallel impedances, so 1 over Z1 plus 1 over Z2 plus a 1 over Z3. And so we can just calculate those then. So that's going to be a 1 over Z1, where Z1 is going to be 2 ohms minus J2 ohms, plus 1 over Z2, so Z2 is going to be 3 ohms. Okay, so here we have Z2. Let me write Z2 down here. So Z2 is going to be 3 ohms minus J9 ohms plus J6 ohms. All right, so we got a J6 ohm and a minus J9 ohms is going to leave me with minus J3 ohms. And then this one was just R3, so that's just a 1 over 10 ohms. Okay, so that is my impedance. So we can flip over to our Octave software. Here and just punch in that number. Or those numbers into the equation there. Alright, so we have Z total now is 1 divided by, make sure you use parentheses, whether you're using a calculator or Octave, make sure you use parentheses. So we're going to have a 1 over parentheses 2 minus J times 2 plus 1 over parentheses 3 minus J times 3 plus 1 over 10, and close your last parenthesis, and so there is my Z total. So we have the Z total there in the rectangular format, okay, which is really preferred, okay, and you can see that it's negative, which means that we have the capacitor is basically leading. So if I was actually going to put this into Blackboard, I would have 1.17 ohms, so it'd be 1.17 ohms plus J. Actually, sorry, it's going to be a minus J. There's a negative sign there. 9,457. So the 7 is going to round up to 6. So 946. So it's going to be minus J 0.946 ohms. And then if we wanted that in polar form, all right, so for polar form, we can use the absolute value of Z, and then we need to calculate the angle. All right, and so we'll use the angle of Z, but remember the angle of Z in using this Octave software at least gives it to me in radians. So I'll take 180 degrees divided by pi radians to get it into an angle, and then I need a square bracket to close that. Oops, not the right parenthesis, but a right bracket. All right, so then the magnitude is going to be 1.51 at an angle of minus 38.9 degrees. So that's going to be 1.51, and this is an impedance, so the units are ohms, and minus 38.9 degrees. Okay. And so that would be the Blackboard form if you were asked to put it in polar form. Now we can calculate our current, right? Using Ohm's law, we have that the current I is going to be equal to, in this case, the supply voltage, because we've got the total impedance, so we use the supply voltage, okay? And those are going to be all phasors there. And so we have just 60 angle 0 divided by our impedance. Now when you do the calculation, make sure you take it out more than just the 3 digits. I'm just going to write down the 3 digits here, but make sure you take it out, or simply keep the values in the calculator for the most accuracy. All right, so we can then therefore calculate our current, which I was equal to 60, and since it's angle 0, I don't really have to worry about the angle, divided by Z total, which I already have in here. So that's the nice thing about the octave. I already got it in here as Z total, so I can just divide by Z total, and that is the rectangular form. But I always want I in the polar form. So I'm just going to come up, use my up arrow key to recall the command to get the polar form of the impedance. And then I'm just going to replace I total with, or excuse me, Z total with I. And that will give us our angle. So that's going to be 39.8 amperes at a positive angle of 38.9. Okay, so that's 39.8, and the units for that are amperes. Okay, so capital A, with an angle of a positive 38.9 degrees. All right, and so that is my total current for this. Now if we wanted to find, say, the current through R2, right, we would just use E divided by Z2. That would give me the current just through this branch. So it would give me the current of R2. Now this branch is series, so the current would be the same. Whatever is going through R2 is the same current that's going through C1, which is the same current that is going through the inductor L here. Okay. And then we could, use Ohm's law. We could calculate the voltage. So if we wanted the voltage across R1, for instance, here, right, we could just first calculate the current through this branch. So the current through this branch would be I1, which would be E divided by Z1. That gives us the current through the branch. And then take that current times the resistance, and that'll give us the current, or the voltage drop, right? So the voltage drop V1 across R1 would be the current through just that branch times R1. Right, so just Ohm's law to find any and all the values here. Just find your currents, and then find your voltages. Okay. Remember, Ohm's law tells us that in general, in an AC circuit, right, the voltage is equal to the current through the element times the impedance of the element. So remember, resistors have an angle of 0, capacitors have an angle of minus 90 degrees or minus J, and inductors have an angle of positive 90 degrees or a plus J.